Welcome to a new edition of 2026 Technical Blog of Norvento Enerxía within the series The Key to Stability. I am Fátima Castro, engineer in the Power Electronics Department at Norvento Tech and Power, where we develop technologies to ensure power stability in grids increasingly dominated by power electronics. This month, we dive into one of the most complex challenges of the energy transition, instability in electric power grids, a phenomenon that can arise from resonances, fluctuations, dynamic decoupling, or loss of synchronization between converters and the grid. To explore this topic, we are joined by an outstanding guest, Professor Marta Molinas, a world-leading researcher in power system dynamics, converter grid interaction, and resonance analysis. Her work has been fundamental in understanding how modern grids dominated by power electronics behave and what mechanism can drive them to instability. Welcome to our blog, Marta.
Thank you very much, Fatima. I'm very pleased to be here. Thank you for the invitation.
We are pleased to have you here. If you are ready, let's begin.
Yeah, we can start.
From a physical and dynamic perspective, how would you define instability in power systems with high penetration of power electronics? What fundamental changes are introduced in the power system compared to the classic paradigm based on synchronous machines?
So in power electronics, from a physical and dynamic point of view, any instability in an electrical system is defined when it is not possible for the system to keep the coherence between, say, the coherence of voltage, current, frequency, and phase. What happens in power electronic system is that these variables are dominated by digital control and by electronic control loops, which makes it to be dominated by a control behavior. The difference with, say, the whole systems dominated by synchronous generators is that the dominant physical behavior was the electromagnetic and mechanical phenomena, or the inertia, the mechanical inertia of the system dominated the phenomena. And that's the difference that we see today, that when a power system is dominated by power electronics converters, these dynamics are not dominant anymore. There is no electromagnetic, electromechanical dynamics dominating the system, but much faster dynamics than those. And there we can say there is a time scale difference of the phenomena, and it's dominated by the digital control, the electronic control.
What dynamic mechanism explain the emergence of converter grid interactions in modern electrified grids?
Yeah, there are several possible origins of these, but say if we can divide it into categories, we can say that it is if we take the case of the grid following converters, for example, that need to track the phase angle of the voltage of the grid, then we can say that the phase lock loop that is doing this job into the grid following converters introduces something that can be called like the dynamic feedback system. And this dynamic feedback system exists because there is a, say, intrinsic time scale problem, or the control loops are in a cascaded form. And this cascade control loops introduces what is called the time scale conflicts or time scale coupling. And if there is insufficient separation of these time scales in the control loops, then we are introducing interactions internally in the converters, but can also be coupled with interactions with the external grid, or the impedance of the converter, the impedance of the grid, or other converters to which this converter is connected. So it is very complex, but basically is we can say, since as I answered your previous question, I said that the dominant behavior is the control, digital control. That means that what is the digital control is introducing is a time delays that didn't exist before in that prevalence. And in control engineering, the instability of a control dominated system is a time delay problem. So basically, this is these interactions of different time delays, different time scales, if we can say in a simple word.
Okay, and related to this, like what are the most common instability modes associated with digital controlling converters?
Yeah, one of those modes, the dominant case, if again I bring the grid following case, is the loss of synchronism. And the loss of synchronism can not necessarily become an instability. Uh, One can lose a synchronism and the converter continues working in connection with the grid, but it is impossible to dispatch a reference value of a current or a power. And why this loss of synchronism can later become an instability is because it will amplify whatever resonances will appear in the system. And the mechanism of this loss of synchronism is several fold. Say one of the cases can be when the grid impedance is very high, and the grid impedance being very high decouples critically the converter from the grid. And then when the PLL is trying to track the grid, it will be dominated by the dynamics of the converter. So then there it introduces a sort of feedback loop with the current controller, which has to be defined in the reference frame that the phase lock loop is inaccurately defining. So that is the main mechanism in grid following. In grid forming, there are different mechanisms because there is no PLL. But we can perhaps discuss that in another.
Yeah, in a following question. How can we differentiate grid inherent resonances from those introduced by power converters? Under what conditions can they interact and mutually amplify?
Yeah, so there are different ways to differentiate them. Um, First, we need to understand what is the range of frequencies of the, say, the oscillations introduced, most of oscillations introduced known by the power converters are generally defined by the passive network architecture or the passive network characteristics of the grid, and they could be measured by not from with a single measurement, but let's say if we take a network and make the converter to be offline or in idle condition, we can measure we can do a frequency scanning of that network. That will be the impedance versus the frequency. And when we observe this plot of the impedance versus the frequency, any peak in the magnitude of this impedance will tell us about a possible resonance point, and that will be intrinsic to the grid because we have put the converter offline. So we can use this information as a baseline of the natural resonance points of the grid. So then the next thing we can do in an online condition is that we measure also the converter impedance or equivalent impedance, and the grid. We have already the grid impedance. So what we can do here is observe the peaks of the converter impedance. And if those peaks are, say, coinciding or near the peaks that we observe in the measurement without the converter, then we can say that the grid impedance, the grid is dominating the resonance in that case. But if this peak is very different from the one that we observe in the grid impedance, then we can say that it is the converter control dynamics that is creating or determining the resonance point. And what can happen is absolutely they can couple together. So if they are close to each other in frequency, then what can happen is that the converter dynamics can amplify the already existing, say, we can say, the already existing tendency to a resonance. It can amplify, or the opposite. It can also, say, damp. It can excite or it can damp these resonances. And that is the good aspect of the power electronics converters, because the controllers can be tuned to do that job.
What mechanism explain the appearance of sub and super synchronous oscillations in renewable plants connected to converters?
Yeah, say subsynchronous. You said first subsynchronous and supersynchronous.
Yes, I said first, yeah.
Yeah, subsynchronous is like, as we have here, oscillations that are determined by the time scales of the control. And supersynchronous generally is believed to be oscillations that are determined by the grid, the passive network characteristics, but not always is like that. But on the low frequency side, we can say subsynchronous is generally originated by the interaction between the PLL and the current control. And this interaction between the PLL and the current controller has been a lot studied. It has proven to introduce a negative damping at certain frequencies. And these frequencies are usually in the range of 3 hertz to 100 hertz. And when there is dominant, dominance by the interaction between the current control and the PLL, will be around 100 hertz to 500 hertz. And this is in converters that have PLL, like in the grid following converters, we can observe this. This we can say is the dominant source of subsynchronous oscillations. When it comes to supersynchronous oscillation, generally it dominates the filter, the input filter of the converter, interacting with the converter impedance itself and the grid impedance. And those are in the order of, we can go from 300 hertz to several kilohertz. But one note of caution here is that when there are several converters interacting with each other, and there is a mix of grid forming and grid following converters, the phenomena is more complex, and we can also experience, or we can also witness, high frequency or super synchronous oscillations that are not necessarily originated only by the passive network architecture or topology.
In power systems with grid following devices, what critical conditions can cause the PLL to lose stability?
Yeah, several typical conditions. One of them is for in steady state conditions, the PLL bandwidth is unable to track accurately the phase angle of the grid voltage. And what will do this immediately, this is what I said before, acts like a feedback system. Why? Because this angle is being used for everything else in the converter control. This angle defines the reference frame, and in this reference frame, the current is defined, the D and Q currents are defined in this reference frame, and that current is being injected again into the network, is affecting the voltage, and again the PLL is measuring an inaccurate voltage. So this can be a vicious cycle, and it is exactly this mechanism that introduces the negative resistance or negative damping that is attributed to the PLL. That is in a steady state. In transient conditions, it can be that the PLL is not sufficiently fast to track the voltage, the grid voltage, because the transient event is much faster. And then this produces a similar effect than in a steady state, but it is highly linear, highly non-linear, because here it is not anymore a small difference of the error between the angle of the grid and the reference frame. So it is a highly nonlinear phenomena that has other consequences and other types of behavior. That is, and another case can be a highly, polluted grid voltage with harmonics, or an unbalanced voltage. That can also be. And a weak grid. The weak grid that we said it before, that a very high impedance of the grid creates this incapability of the PLL to track this angle.
You already started with the next question that I just How does grid weakness influence the emergence of instability phenomena?
Yes, the weak grid, in the grid following case. Again, we have to make it clear that this happens in the grid following case. And if we assume that the definition of a weak grid is a high impedance of the grid, then this high impedance of the grid, what it does is decouples the converter from the grid. So the PLL sees a much higher angle, phase angle that has to track. This is number one thing. And there is an analogy that makes it maybe easier to understand this amplification effect that is produced because of the weak grid, is that in a grid following converter, the grid impedance and the converter impedance appear shunted at the point of connection. And a shunt connection between a very strong impedance and a smaller one will end up giving us that the converter impedance dominates the dynamics here. And what does that mean? It means that the PLL is part of this converter impedance. I'm talking about the converter equivalent impedance. And when the PLL is not able to track properly the phase angle of the grid, then only what only what the converter is injecting will dominate the behavior. So it is at complete decoupled from the grid, and at some point, this because of the amplification effect of the negative damping of this, we may lose stability of the system. So that's how the PLL works.
And now moving to grid forming converters, how can they improve stability and what new challenges do they introduce?
Yeah, see, different from the grid following case, the grid forming main advantage is that it actually creates a grid voltage, or it creates a voltage, which was the weak point of the grid following. By creating a voltage doesn't need a PLL to synchronize. It synchronizes in a more, say, natural way by using power synchronizations, power loops, and then it has all the advantages that are weaknesses in the in the grid following. So it doesn't have the problems of the grid following for tracking the voltage. It can also introduce synthetic inertia, although one disadvantage of the grid following is that, I mean, in general, in converter, is that it does not have inherent inertia. Um, a problem that can arise in grid forming is that the weakness comes in a strong grid rather than in weak grids. So we have observed in our studies, say, these more difficulties to keep stability when there is several grid formings interacting, or say we can say that the interoperability of grid forming converters in strong grids becomes a problem there. Power sharing becomes a problem. There has to be a clear coordination because they are using droop type of controllers of power in this case. Therefore, there is a lot of sensitivities in the tuning of these troops and in a multi-converter system. So grid forming weaknesses comes in multi-converter operations and the different type of grid forming implementations that may exist and whether they are compatible with each other.
Okay. Nowadays, which methodologies do you consider most appropriate for analyzing stability in hybrid AC/DC networks?
You are talking about small signal or
Yeah, yeah, small signal or modal analysis or EMT.
yes. Say there are categories there of analysis depending on what one has at hand and what one wants to know. Analytical methods like model analysis or state space analysis exist, and they are relatively good, but say we always have to linearize in these analytical models and to have we take several assumptions of the details of the model, And we need to get a lot of information for doing these analytical studies. So we need to have all possible information we can get from the control tunings, the control parameters, etc. And they can provide analytical insight, and they are usually used before deployment. And then the second category would be the measurement based analysis, or small signals based on measurement, that need less of analytical resources, but they need to be validated against analytical models and simulated models. One example of that is the impedance based stability analysis, that can be very resourceful, especially when online, because it is measurement based and we can get snapshots of the stability by using simple techniques like the Nyquist stability criteria or body plots analysis. And it can give us insight into the stability conditions of the network without having much detail of without having to have all the knowledge of the parameters of the network, but still we need to have some knowledge as well what type of control loops are being used. We need to take some assumptions, so it's not completely a black box system, but it is very useful if we have a certain amount of information about the control architecture of the system. And then there are the nonlinear techniques and the electromagnetic transient simulations, that these simulations offer very deep insight into the nonlinear dynamics and detailed time responses of the system. But they are more used before deployment, I say. During operation, then real time, say, diagnostic tools will be more useful, like, for example, the impedance measurement that will not require much knowledge of the network.
To what extent do current EMT models accurately reproduce real behaviors under instability conditions? What major limitations still constrain current approaches?
Yeah, electromagnetic transient simulation software, many of them exist, but and it is very much used into the research to understand states that are not possible to get into analytical models, and that are not possible to obtain from just experimental work. So it offers some flexibility into a larger state space investigation or exploration, we can say. The, the main advantage is that it gives us more information depending on the fidelity of the modeling, because the fidelity is fundamental here. So, how much fidelity we can reproduce the controllers and all the physical components of the system, depending on that, we will get better results than we can get in an analytical model. Usually the steps is we go first into analytical model, and then we try to see the simulation with higher fidelity give us more or less similar behavior. The problem will be that when we have several converters, this becomes untractable. When the scale of the system becomes larger and larger, then it is not, say, practical to use EMT simulations. There should be like more tractable models in that sense. Another problem is the time steps. And say numerical stiffness can happen. As far as I know, the EMT models that exist, they are not so flexible of changing the time steps depending on the dynamic that one wants to observe. If I put a very fast time step, then the model will be doing that even for steady state calculations, which is not necessary. If I have a very slow time step, then I will lose the very detail of the fast scale dynamics. So that's the limitations of that.
Among the available mitigation strategies, which control techniques have proven most effective in suppressing converter-induced instabilities? I'm talking about techniques like virtual damping, synthetic impedance, active loop.
Yeah, I would say that I would recommend the first one because maybe I am biased because I'm working on that a lot is the impedance based analysis. And why I say that? Because every system we have, regardless of whether it's electrical machine or digital control dominated, we can always find the equivalent impedance of this system. Once we find the equivalent impedance of the system, and then we have the grid impedance, and then we have the rest of the system impedance, we can use circuit analysis, which everyone is familiar with, to find the stability, to identify the stability of the system. So, and then every action like virtual damping, passivity enforcement, synthetic inertia can be reshaped or can be implemented by looking at this impedance behavior. So damping, virtual damping can be introduced in the current loop, in the voltage loop, in the power loop, and they all work in different time scales. So damping in general is introduced via the controllers, and this can be portrayed or seen directly on the impedance of the system. And I always recommend impedance reshaping for counteracting instability problems. And impedance reshaping can be simply, say, be a damping, a retuning of a parameter, introduction of a damping. Another way to look at this way, at this how to stabilize a system is to discuss it from the point of view of the passivity of the network. We have a network on the grid side. The converter can be represented also by an equivalent impedance, which I will say R plus JX. That's the impedance of my converter, whatever converter it is. And before I mentioned that in the grid following, this R is a negative R, which is not desirable because this negative R is a negative damping. If somehow I can convert this R into a positive R always, that is what is called passivity enforcement. And that again, I can see it through the impedance because R plus JX is an impedance. So if I can convert minus R into R for all frequencies, I am doing something that is called passivity enforcement. And this art of omega can be internally a current, say, an internal loop damping, like a current loop damping, like a voltage loop damping, or a power loop damping. Everything can be, say, translated into an impedance and passivize that impedance. So enforce that the converter will always have a positive resistant equivalent into his equivalent impedance. So that I will say is, and grid forming is one such. So if we analyze grid forming by using this concept of the passivation, we will see that comparing grid forming and grid following from the point of view of this impedance, the grid forming will rarely have this negative. It may have it when it is in a certain particular conditions, not very common.
When multiple converters interact, what challenges arise regarding collective stability in highly electrified networks?
Yeah, so one of the things is that we don't know what is inside the converters when there are many vendors. This is the number one conflict. Some vendors will sell converters with grid following capability only. Some others will sell with grid forming and mode switching. But knowing what is exactly behind the converter control is a problem, is the main problem. When you put them together in a network that is operated by a third party again, then this converter will operate as they are given there. And there will be another factor that is the grid impedance and the rest of the system in which they are. Some of them will be grid forming, some of them will be grid following. Maybe grid following dominate. We don't know that. This depends on the structure. And this interaction is the main challenge Again, all of these converters can be represented by their equivalent impedance, and then we will have a network of several impedances that will change in real time. And the problem becomes of stability of a network that is constantly changing depending on the control structure that is dominating. So if there are all grid forming, one may think, yeah, everything will be stable from now on. But it is not the case because the grid forming, since they are emulating the synchronous machines in general, they will inherit the same problems of connecting synchronous machine in parallel. So there will be circulation of currents, parasitic circulation of power among them if they are not well coordinated. So we solve some problems with the grid following, but we introduce other problems with the grid forming. So a very close follow-up of these interactions is very important.
In your view, is there a point at which increasing the penetration of power electronics produces instability more likely? Or is system stability primarily determined by the quality of the control design rather than the number of converters in the grid?
Is not determined by the number of converters. Is a problem that depends on the system one is looking at. So every network has so many variables and parameters that one has to take into account. And for like in the past when we had synchronous machine, it was the same. It's not there were instabilities there also, and it did not depend on whether you know what type of machines were dominated or not. So there is always an instability point, and it can always be calculated, and it is very much depending on the conditions of the system at that particular moment. That can be topology of the network, number and types of converters control in that moment. It's not really, I cannot say that there is a penetration rate that will create the problem at all. It is more depending on what is the situation that was at that moment critical, what was the dominant behavior that actually say drove the instability into that point.
What role should real-time platforms and hardware-in-the-loop testing play in detecting and anticipating instabilities?
Yeah, this hardware in the loop, they give us opportunity to have a hardware connected with, let's say, a control that we would like to test. And what is the main advantage of that is that what the other solutions do not provide, like analytical model and simulation models I mentioned before, there is this, say, calculation stiffness, for example, in the EMT models. Once we get the hardware in the loop thing, we can actually test the interaction between the digital controllers and the physical hardware for the first time. And that gives very much advantages on identifying instability modes that are originated by that interaction. Is one step farther into what we could do with analytical and simulation models with high fidelity. Now the fidelity is the highest possible because we are testing the most important component, which is the digital delays, and not only digital delays, quantization, sampling effects, discretization, all of these will be very well tested in this. And we can also make safer experimentations because we can test many models, many control types, and how they interact with the physical hardware. So those could be the advantages here.
Which research lines do you consider most promising for mitigating instabilities in grids with renewable penetration approaching 100%?
Yeah, there are many that I can mention here today, but I would say one that is really pressing, and given the experience of the recent blackout in Spain, I would say that very good techniques for predicting, for anticipating, and for giving early warnings would be very, very useful. From the point of view of the usefulness in real life, that will be. But once you embark in such a task, you will have to embark in all of the things we were discussing today. You cannot avoid that. It is one of the most challenging things to find this, say, prediction, anticipation, and early warnings. And early warnings means that we have time to react, to do some changes in the system, like it didn't happen in the Spanish blackout. Say, people knew more or less what was happening, but then suddenly control was completely lost. There was no possible, say, intervention that could save the system, and the system went to a collapse. So early warning, and I think now with the AI tools that we have at our hands, it is very possible to identify all possible instability modes, because all of these instability modes that we are witnessing from more than 2 decades ago, when the very first phenomenon of instability appears in 2011 in the Horns Rev wind farm, say, all of these are new to the system. And this is why it creates confusion, because the operators were used to synchronous machine and they just dismiss this type of oscillations. And another way they react is they don't want this system into their system because they don't know how this system behaves. So, and very thorough identifications of the new modes of oscillations that appear because of power electronic system is one of the things that I would say, with the power of AI today, we can do this. We can do massive simulations of system topologies, system shares of grid forming, grid following, and use features, for example, features in the frequency, features in the voltage, but features in the frequency will be one very interesting starting point, because the frequency always reveals first what is going on, first than anything else. The frequency is like the blood that is circulating through the body of this grid. So the blood usually has all this information that first, before anything else happens in the body. So the frequency should be a diagnostic starting point for the grid. And with AI, this is possible to do. There is some starting works already seen on this, in which just by looking at the frequency, we can differentiate different modes of oscillations that are created by power electronics, and even differentiate it from, let's say, for example, electromagnetic, electromechanical, or torsional oscillations, because I forgot to mention that in the low frequency oscillation, we can also have a mix of torsional oscillations from the multi-mass models of, for example, wind turbines or thermal generators. And they should be clearly differentiated from PLL dynamics. Otherwise, we cannot correct. So this type of research, I think, is extremely necessary to anticipate and take corrective actions. And say ramificated from that, then there will be grid forming, interoperability, all is secondary. The main is to kind of have prediction systems. Yes, that is my opinion.
Okay, so prediction is most important. Thank you, Marta. Thank you very much for joining us and helping us delve into such a key topic for the stability of the power system.
You're welcome. I'm very happy to talk here today.
Thank you. And to all those following us in the 2026 technical blog of Norvento Enerxía, we invite you to stay tuned to upcoming interviews about the technical pillars of the energy transition. See you next time.